is that, let me turn this off. Exam 3 is on Monday. And the topics are everything up through linkages. And since linkages really contain just about all the other stuff we've done, you can be pretty confident that it's going to be a whole test of linkage-related questions. Okay. Anybody have any questions about the test? Yeah.
Do we know how many questions are going to be on it?
No, because it sort of depends on the kind of questions. If I did a full linkage question, there would probably just be one, you know. Sometimes I also do like break problems up into pieces because, so if I did a linkage question where you were going to go all the way through, it would have to be a fairly simple one. I could do more complicated questions if I don't make you go all the way through and say like, draw the free body diagrams and then give me the constraint equations, you know, then that can save some time so I could ask more. So it just depends on what kind of questions I ask. But yeah, be ready to separate the constraint equations from the Newton's laws equations, because I've done that several times. Just say like, give me the constraint equations for this, you know, in terms of these variables or whatever. Any other questions? Okay. Does anybody have any, I'd be happy to go over a linkage problem or two if anyone has one that you'd like to see. No. Which one? Yeah. Oh, I didn't ever assign this one, I don't think, right? That one's kind of a mess. It's confusing to figure out the geometry and stuff. I'm planning to replace that. So let's not do that. I did in class one day do a 4-bar linkage thing that was a lot easier to interpret. And I don't remember what day, but it wouldn't take too long scrolling through the notes to find it. I think it's early on in my lectures on linkages. So maybe look at that, I would say. Any other questions? Any other problems you'd like to see? Okay. One thing about this one, well, we didn't do it, but I gave you, this is one thing that's different than the other problems. I gave you an angular velocity of one of these bodies, and I didn't give you the angular velocities of the others. But if you think about it, just think about it physically, like, say if that wheel is moving with a certain angular velocity, that defines angular velocities for the other bodies, right? And I didn't give you those. So how would you figure those out? I haven't asked you that. I'm not going to ask you that on the test, but I think for an overall kind of understanding, this is kind of I think it helps you sort of think in terms of constraints and stuff. Well, the way you would figure it out is you would say, you would say the acceleration of this point, okay, so think about the way you do constraints, the constraint of that pin, you know? We would say the acceleration of that point on this body has to match the acceleration of that point on this body. That's how we do the constraint equations. To figure out the angular velocities, if this is given an angular velocity or the middle one or whatever, we'd say calculate the angular velocity of this point according to this body. Calculate the angular velocity of that point according to this body. Okay, those have to be the same. The angular velocities just come from circular motion and relative motion. Okay, and then you say, and besides that, this point on this body has to have the same velocity as that point on this body. So calculate those instead of equal. You get a set of constraint equations that have, and those constraint equations, because it's circular motion, have like an omega 1 and an omega 2, and then this given omega 3, you know? And it allows you to back calculate what those are. So instead of those being given, those are variables. You set up to say the velocities match at these points, and then you back calculate the required angular velocities of the bodies. You won't have to do that on the test, but like when I give angular velocities for everything in a problem, that's what I have to do to get it if it's a complicated problem. And if I don't, that's how you would go about finding it. Mm-hmm. Okay. What? This one? Okay. So let's see, it's 3 meters and 1.5 meters. Oh, and also, I think I might have a solution for this. If you look at the homework solutions, I think it's in there. One thing is the angles need to be given, and they weren't, but in the solution, it tells you what angles I'm using. So this one is 10 degrees from the horizontal, and this one is 10 degrees from the horizontal. Do you think it would be helpful for me to go through it, or you want to just look at the solution of that? I'd be happy to do either. Okay. And then, yeah, send me an email or talk to me later today if you're around, if anything's confusing. I have office hours from 12 to 2 today. Okay, here's what I want to do today. This is going to be amazing. Yes?
Just a quick question.
Yeah.
Are we going to have to deal with problems that have, like in terms of like a horse and cowboy situation?
No. Right. That's super important.
I was following up.
Oh, I'm sorry. I got so excited.
Where there's like, let's say a horse and a cowboy connected, but then there's another beam or whatever that's connected to the cowboy that it's also a horse and cowboy situation. I don't know if you understand.
Yeah, I know what you mean. So are you talking about on this test or overall?
Both, yeah.
Okay, on this test, so you could imagine like this crazy nunchuck looking thing like this. Well, definitely not on a 50-minute test, maybe on a weekly assignment, you know. But the process would be exactly the same on this as it is if there were only 2 of these bodies. So you calculate, you use Newton's laws for this, this, and this, and we can plan it all out. Fixed point here means we're not going to use Newton's second law, So this is one equation. Neither of these two have fixed points, so that's 3 and 3. So we'd have 7 total equations from Newton's laws. And then the constraints that we would have say that this body and this body have to agree on the acceleration of that point. So that's 2 equations. This one and this one have to agree on the acceleration at this point, so that's 2 more equations. So we have 7 plus 4, 11 equations, which means we're going to have 11 variables there. And that's why it wouldn't be on a 50-minute test. I wouldn't, it would take too long, but conceptually it's no harder. I mean, anytime you have 2 bodies connected at a pin joint, you just use that requirement that the accelerations match at that point.
Okay, so you could really just have like n.
You could have a million, yeah, exactly.
Okay.
Yep.
You just have a really large matrix.
Right, and if you take this and connect it to another pin joint somewhere, you have a 4-bar linkage. And we've done a problem like that. Okay. So today, here's what we're gonna do. Well, I don't know. We're going to do this carefully. I think I sort of sketched it out once before, but what's the acceleration error that comes from using a coordinate system fixed to the Earth? Okay. So the Earth is spinning. We know that means it's not an inertial coordinate system, but it's spinning very slowly. So, we know we can get away with it's very close to being an inertial coordinate system, but let's calculate what the error is, okay? Okay, so here's the Earth. And this is the coordinate system I'm going to use. That's the center of the Earth there. Okay. And we're going to say the radius of the Earth is 6 times 10 to the 6 meters. And it is rotating this way. And we are going to assume that the angular speed of rotation is 7 times 10 to the minus 5 radians per second. Okay. On this coordinate system, we're going to assume that the position vector is the radius of the Earth times cosine and sine of some angle. So we'll see the effect of latitude. Okay. And we're going to track an object that's on, near the surface of the Earth. With a true, so like if you had an inertial coordinate system measuring its motion, velocity vector of Vx, Vy, Vz. Okay. And a true, we're going to assume that's a constant velocity, and so the true acceleration is 0. Okay. So how are we going to, so I say we're going to measure the acceleration error. How do you think we're going to, like, what are we going to do to measure that acceleration error? So we know this is a rotating coordinate system, right? So we know we have that the total acceleration is equal to the observed acceleration plus omega dot cross p plus omega, 2 times omega crossed with the observed velocity plus omega cross quantity omega cross p. Okay, so when I say we're measuring the error, what two things am I comparing?
A observed and B.
Yeah, exactly, perfect. So we're comparing A observed and the true acceleration. The true acceleration is 0, so whatever vector we calculate for A observed is error. Okay, yes?
Isn't the omega dot and the 2 omega cross B?
No, it's this. Yes?
Might be remembering wrong, but I thought it was E and R in the equation, but I don't know.
In this equation, it's only P's, but usually when we calculate V observed and A observed, we have to use R, because usually that's a circular motion. Okay. All right, well, we got a lot of this stuff. Let's just start listing out what we have. Omega is 0, omega 0. Okay. And that is the correct, if that y-axis is pointing north, that is the correct orientation because the east sees the sun first. I'm just saying because that's how I had to think about it. Oh, the east sees the sun first, okay. And then omega dot, we're assuming that's constant, so yeah, if all of a sudden there was like a big change in that, it would make our lives very chaotic. And our P is given. So that's, and we'll put in the numbers after, but I'm just going to leave it like this because it makes it simpler. But what about, so A observed is what we're trying to find. Okay. But what about V observed? Well, for that, we haven't really had to do this before, but now we can say that, remember, the velocity, the true velocity in a rotating coordinate system is the velocity observed plus omega cross position. Okay? So, and we're given the true velocity, so we can use this to back calculate the observed velocity. Okay? The true velocity, I just called that, so we got Vx, Vy, Vz. That's what some alien at rest in the middle of the universe with a really good telescope sees as the velocity. Okay? And he doesn't have to be at rest. He could also be moving with a constant velocity.
Can he be awake? He's not resting.
Aliens are super lazy. And that's equal to V observed plus 0 omega 0. Are you excited to find this out? You've always wondered, right?
Always. Can't sleep at night.
I've been dreaming about it.
Yeah.
Okay, but now I'm gonna think about,
Okay, everybody.
now I'm gonna think about the Earth's, revolutions around the sun.
Yeah.
And the solar system's movement. and
Yeah. Well, we're gonna,
Rift of the Milky
Right.
Way and all that.
I hear you, but we're going to guess that each step out produces less air in the acceleration. I think that's reasonable, but I haven't calculated for I've been meaning to do that, but I haven't done it yet. But let's go on that assumption for now. The biggest error in acceleration is the spinning. The second biggest is going around the sun. The third biggest is the solar system going around the galaxy or whatever. Yeah.
So is this, in terms of errors, you have the gravitational forces of other planets in the sun. Would that produce a different error in acceleration, or is that already?
No, the forces are built in. Like if you're just doing kinematics, you've already built in all the forces. You're just measuring the motion. You know what I mean? Okay, so we got to hurry. So we got this crossed with the position vector. This thing says 0. 0. Well, that's easy. And then negative omega r cosine. And let's always put the bigger things first. Okay, so we'll have negative r omega cosine theta. Okay, so we remember r is huge. It's times 10 to the 6. Omega is tiny. It's times 10 to the minus 5. So we'll get to what those are later. And so our V observed is Vx, Vy, Vz minus r omega cosine theta. Okay? And now we have everything we need to go to the acceleration equation. The true acceleration is zeros. And that's equal to the observed acceleration. Question?
Wouldn't it be plus r cosine, or r omega cosine theta, because we're subtracting a negative?
Where's the negative? Yeah. Thank you. Here. Yes. Ooh, that was close. So 0 is equal to A observed plus this thing, which is 0, plus 2 times 0 omega 0 crossed with V observed, which we just figured out, plus 0 omega 0 cross quantity 0 omega 0 cross r cosine theta, r sine theta, 0. When Rob said that thing about, like, that derogatory thing about people just sitting and calculating stuff, didn't that feel like a little personal towards me?
No. Did kind of look at you a little bit.
And so these two together, so we got 0 for x, 0 for y, and negative r, oh, well, we already calculated that, negative r omega cosine theta. And so these all together, this last term is in the x direction, negative r omega squared cosine theta. Does that look right to everybody? And then 0, and then 0. And this one, for x, we have 2 omega, I'll rearrange it in a second, times the quantity Vz plus r omega cosine theta. For y, we have 0. And for z, we have minus omega Vx. Yes, thank you. Thank you. And so I'll rewrite this first. So we got 0 is equal to A observed plus 2 Vz omega plus r, now 2r omega squared cosine theta, 0, negative 2 Vx omega plus negative r omega squared times cosine theta, 0, 0. And so finally, A observed is equal to R, oh, well, look at these two things. We got a plus 2r omega squared cosine minus one of them. And so we get negative r omega squared cosine theta minus 2 Vz times omega, 0, positive 2 Vx omega. Okay, let's punch in these numbers, which are also sort of approximations, but so we got 6 times 10 to the 6 times 7 times 10 to the minus 5 squared. So that says minus 0.0294 cosine theta. Minus 1.4 times 10 to the minus 4, that's just the 2 times the omega, times Vz, 0, and then positive 1.4 times 10 to the minus 4 Vx. And that's all error because we were assuming that this thing has no true acceleration. Well, where is this going to be? So we have this one dependence on the cosine in the x component, and that term looks like it'll most often be biggest when you're at the equator, because that theta is equal to 0. And you can see both of these two components of observed acceleration depend on how fast this thing is moving. And they don't depend at all on how fast it's moving vertically along the axis of rotation, but it does depend on the components in x and z. Isn't that cool?
So what is Vx and Vz?
We're just assuming that we're on the Earth coordinate system, we're tracking the motion of something with a random constant velocity.
Okay, so.
True velocity.
It's not moving, you just ignore those terms.
Right, that's right. And so if it wasn't moving at all you would see is on the equator, you'd have an error in the negative x direction, which would be like gravity. You'd have an extra amount of gravity that's equal to 0.0294 meters per second squared.
Unless you're on the North Pole.
Yes, that's what I meant to, at the equator, if it's not moving, right. If you're at the North Pole, it would be 0, right?
That's where we should do our experimentation.
If you're at the North Pole.
Yeah. Well, that just means.
Yeah, but then you still have to worry about that z.
And it won't be moving.
And only do experiments on things at rest. And then,
Can't do it.
right, yeah. Come on, you guys, this is like, you've always wondered, like, how this thing is spinning, how can we know, how can we do experiments and depend on Newton's laws? This is why, because in almost every case, the errors are small, but this is how big they are. So next time you do an experiment in some lab or whatever, bring this up, tell them, like, by my calculations, this is the error in the acceleration. Are we going to account for that?
So if you get the exact right answer in a kinematics lab, you're actually wrong.
That's true. That's true. That's very true. Well, we're at like latitude of 40. I think that means that theta is 40. I think that's what latitude is, right? So.
Well, sure. Is it latitude positive and wait, no, that works.
Yeah, it works. Right. I think that's what latitude is. No, I like the thought process.
And I was like, wait, no, that is how.
Yeah, that's how angles work also. I think that's all latitude is. So you can plug in, maybe we're 45 or something. So, okay, well, so plug in 45 and you get this times 0.0707.
Fun.
Yeah. Okay, thank you. Test on Monday.
Are you doing the solar system?